Now let's look at the review problems from Chapter 13, which is on page 656. The first problem we want to look at is number 3. Number 3 says an outfit consists of a shirt, pants, tie, and jacket. If you have 5 shirts, 4 pairs of pants, 6 ties, and 2 jackets, how many different outfits can you make? So what I'm going to do is I'm going to use the slot method, and I'm going to say, all right, I'm putting together a shirt, a pant, a tie, and a jacket. And I have 5 shirts, I have 4 pants, 6 ties, and 2 jackets. And to find the total number of outfits I can make, what I'm going to do is I'm going to count this by multiplying all of these together. And that'll give me the total number of different ways in which I can put those together. So 5 times 4 times 6 times 2 will give me 240 different outfits. That's not one that you can do with a combination or a permutation. It's one that you have to do with the slot method. The next problem to look at is number 4. Number 4 says a rock climbing club has 14 members. If the club wants to select a president, vice president, and treasurer, all of whom must be different, in how many ways can this be done? Well, this one can actually be a permutation or a combination, and we have to determine which one it is. And in order to determine that, we need to ask the question, does order matter? And in this case, since we're choosing somebody to be president, vice president, and treasurer, the order in which we pick them is going to be important, because if we pick person A to be president, person B to be vice president, that'll be quite different than if we did that reversed. So, since the order matters, it's a yes to that answer. It's going to be a permutation. So we can do a permutation of, we've got 14 members in the club, and we're picking 3 people to be on the different, in the different offices. So if we do that on the calculator, you would put in 14 first, then you'd go to your math menu, go over to your probability menu, go down, choose permutation, and then plug in 3 and enter, and you'll get that there's 2,184 ways that that can happen. Or if you were doing the slot method, you would say president, vice president, treasurer. There are 14 people that could be president, 13 people that could be vice president because we already picked one for president, 12 people that could be treasurer because we already picked these 2 offices. And since order matters, we're not overcounting anything, and so we can just multiply those out, and you'll get the same thing that you got here. So that's number 4. Number 11 says the research director of NASA must choose 3 experiments for the next space shuttle. If 17 experiments are proposed, in how many ways can this decision be made? Well, again, this is one that can be a permutation or combination, and we need to ask the question, does order matter? Well, for this one, we're picking experiments to go up into space, and it doesn't matter if that experiment got picked first or second, it's still going up into space. So our answer is no, it doesn't matter what order it got picked, so it's going to be a combination. So we've got 17 different experiments to choose from, and we're choosing 3. So again, we go to the calculator, we hit 17, go back to the math menu, probability, combination, choosing 3, so there's 680 ways that can be done. Or if you did that using slots, you could say, all right, here's my 3 slots for those experiments. There's 17 experiments that could be picked first, 16 that could be picked second, 15 that could be picked third. Since order doesn't matter, all right, I'm overcounting these, so I multiply this out, but I take the 3 experiments that got chosen and say that they could be arranged in 3 times 2 times 1 different way, and they all are still the same 3 experiments. And once you do that, you'll get the same answer. The last question is number 12. And it says a password for a computer consists of 3 different letters of the alphabet followed by 2 different digits from 0 to 9. How many passwords are possible? And on this one, I wouldn't go with permutations or combinations. I would just go with the slot method. And what we're doing is we are doing letters, 3 different letters, followed by 2 different digits. And the key there is that they are different letters of the alphabet. So there are 26 letters that could go in the first slot, but in order for it to be different, there's only 25 that could go in the second, only 24 that could go in the third. Similarly, with the digits, there are 10 digits that could go first, and then there are only 9 digits that could go second, because we are making sure that they're different. And then we would just multiply that, 26 times 25 times 24 times 10 times 9, and we get an answer of there are 1,404,000 different passwords. And those are the problems from Chapter 13.